Okay, so I'm just waiting for the YouTube live to kick off. Here we go. Right, we are on. I need to mute myself so I don't actually hear myself talking as a massive echo. Good evening, ladies and gentlemen. Welcome to, well, happy hump day, as I mentioned earlier in the day on Instagram. It is Wednesday, the middle of the week. That means we are halfway to the weekend, which is awesome. But more importantly, what that means is we are on chemistry day. Hey, Ryan, good to see you back, mate. Okay, really pleased to have you here tonight. Basically, what am I here doing tonight? Well, I'm here just to, I don't know, henceforth and chemistry. All right. So essentially, I am just here for you to pillage and plunder whatever information I've got in my head about chemistry and about tailored tutors in general. So basically, it's a case of fill your boots. I mean, I've got some example questions lined up, just so we can have a look at some of the different questions that you could come across in the A-level exams. Oh, straight in there, Uzwa. Hi, I was wondering if you could explain equilibrium, especially the effect of temperature. It never makes sense. We will definitely get to that, all right? So that is my first question. I'm going to write that down. Just give me 1 second. Okay, so equilibrium and temperature. So I take it you mean Le Chatelier's, Uzwa? Le Chatelier principle? There's a bit of a delay. Okay, so, if I ask a question and just move on, don't worry, I'm not just ignoring you. All right, so make sure you type as quickly as you can, but even though there's still like maybe a 10-second delay or something before I see those comments up on the chat. Okay, Ronnie's joined us. Hey, Ronnie, how are we doing? Good to see you on a Wednesday. I know you're looking forward to doing your math session tomorrow night, even though you did a Brucey bonus math section last night as well. Okay. So, right. So, you know what? I'm just going to henceforth and kind of babble on about something just to kick off with. Okay, Yasmin, have we got one on the Arrhenius equation? I can certainly have a look for you, Yasin. Okay. Yeah, equilibrium. The second one for equilibrium, yeah, we can definitely do that. Just being like my normal chemistry geek self and Apple fanboy, I was just watching the first part of the what do they call it, like a keynote speech that Apple announcing all the new iPhones and Apple Watch and stuff like that. But what I found really interesting was they had a huge kind of push on environmental impacts of creating all this new technology and so on and so forth. And they run all their stuff, all their stores and all their data centers and everything like that are all 100% renewable energy, which is absolutely amazing achievement for a company the size of Apple. And all the components they're using, they're trying to minimize it, digging up new resources, obviously in other countries to get the resources to build the iPhones and the iWatches and the Macs and stuff like that. It's a huge, huge push. They got a lady with a cardigan on who's obviously really concerned about the environment to talk about it. I just thought it was absolutely amazing. I love that material science that goes into new tech and stuff like that. Massive geek for it. I'm ignoring your questions. Could you go over benzene and isomerism, please? Okay, so benzene and isomerism. I haven't forgotten about the Arrhenius one, but maybe that's one for another night because it's a bit of a heavy one. That okay? We want to try and keep it light. Isomerism. If you got any particular type of isomerism you want me to go over. Lots of A2 stuff. I'll do my very, very best. Another request for the Arrhenius again. Okay, so we can have a look at that. Not my favorite thing, I will admit that, but Arrhenius equation, dim problem, no problem. So you probably noticed I've opted for the baseball cap tonight, just for giggles, really. Changing it up with the old flat cap and less farmer, more kind of like an American lumberjack this evening. So there we go. Can you go over proton and carbon NMR questions? We can certainly see if we can find some on that. Okay, so H plus CNMR questions. Yeah, we can go through that. I mean, do you want me to go through explaining what it is and how it works and what we can look for in terms of those? We can do that. Stereoisomerism, yeah, absolutely. That's a type of isomerism. Brilliant, we can do that. So that'll be EZ, and of course our optical isomerism. So we got a good mix of stuff here to kick off with, ladies and gents. So I'll tell you what, before I do, I mean, I know some of you have already been in the other YouTube lives that we've been doing. Hey Jay, hey Selena. Is there, does any of you, or do any of you, I should say, have any questions about tailored tutors, about signing up, about what we do, about, you know, what the subscriptions are, what the differences between them, anything like that? And you know what? And if you haven't right now, that's fine. If you think of anything at the end of this little tutorial that we're doing, then you can always ask me at the end there. But I'm just going to throw this open right now to see if anybody's got any questions. You know what? If you haven't, just stick a quick no in the chat, so at least I know that you know, you're just not wandered off, or you know, or you are actually paying attention, but you just don't want to ask anything. Alice, anything on mass spec? You know what? We can go through mass spec. I can give you some ideas. Are you talking about elemental mass spec, so like first year stuff in terms of that, or are we looking at organic mass spec, where we're using mass spectrometry and the fragmentation of the different molecules to help decide on what the actual formula of the molecule is? So what do you mean by mass spec? What type of mass spec? Thanks, AJ, too, getting involved. I like that. Mass spec. I'm going to make a note of mass spec as well. Has anybody had any homework yet? I mean, Carl, you guys have been in for maybe, what, a week? Less than a week. Anybody actually had any homework yet? I was really mean when I was working in the college. Like, first thing I do is like, right, we're starting this. Here's some new stuff. Here's the homework on it. I want it next week. I'm just horrible like that. What can I do? Hey, what can I say? Oh, absolutely. Yeah, Ronnie's on there answering questions if you got about TT. Alice, brilliant. Okay, looking, excuse me, like working out a compound out from fragmentation peaks. So fragmentation is a huge diagnostic tool when it comes to identifying organic compounds and shizzle. So we'll do that. Okay, so fragmentation. So a few people asked for a few different things here. I'm going to leave because Arrhenius, like I say, is really heavy. You know what? We can have a look at that next week. Maybe we can focus on that next week. I can prepare more stuff because those questions are actually few and far between. I don't want to waste your time with 15 minutes me looking for a particular question through all the exam papers that I've got access to. Okay, so I'm not ignoring Arrhenius. We can do that next week. There's another free YouTube live on Wednesday next week, so maybe we'll get to it then. But you know what? We will start with some of this equilibrium stuff because it's not just important for your first year or AS, it goes right the way through. Okay, right the way through, right into year 2, where we have to start using it when we're looking at weak acids, when we're looking at, well, acid-base equilibria as well, when we're looking at ligands and complex ions. It's all in there too. So, you know, Le Chatelier's runs right through. So I'm going to go ahead and I'm going to share my iPad screen now, and I'm just going to go henceforth and, you know, just blurge Le Chatelier stuff. Okay, so I'll keep one eye on the comments. So if you got any questions as I go through, like I said, bear in mind the delay, then I will come back and I will answer it. So Le Chatelier's, here we come. Share screen. And we should be sharing screen any moment now. Otherwise, I'm just staring into blank space. Here we go. We are on, I think. So just while that's loading up, oh, there we go. We are in. So this is just my rough list, of course, of things that you guys wanted to talk about tonight. All right, so let's see if I can just make this a bit smaller on my screen. Oh, apparently I can't. Okay. So I'm just going to move this over to one side. Hey, Rich, how are we doing?
Hey, folks. So I'm a little bit late. I was in a bit of an important meeting, and I decided that I had to finish it off as opposed to come and join you guys. But I knew Rich was here to handle you, so I'm going to just pick up some of the comments on YouTube. Anyone's got any chemistry questions, obviously, let's submit them. We can deal with them at the end. And Richard, what's going on? Fill me in.
So basically, I just started a little bit of a rant about the new Apple keynote that I was watching just before, because they had a big segment on the environment and what they're doing to minimize their impact on the environment and stuff, using new materials. Really good chemistry stuff at the heart of that. So just thought I'd have a little bit of rant about that. And yeah, people have just been straight in there, no messing, asking for me to go over different topics, as you can see by my my list here, my scroll. And these are the things that we're going to be going through tonight. And hopefully I can find some questions as well. Maybe do a cheeky mole count to finish off. So yeah, plenty to do. It'll keep us busy for an hour at least.
Sweet.
Awesome. Right. So where do we start? Le Chatelier's. That's where we're starting, folks. All right. So Le Chatelier's principle and equilibrium. So you know what? I'm just going to go on to another page here. So if you want to make any notes on this, go ahead and do so. You know, this is all going to be recorded. It's going to be replayed on YouTube. That's all good. So, you know, you can go back and rewatch this if you really, really want to. Now, of course, equilibrium, that's all based around this symbol here. Okay, where we have, if I can spell it, a dynamic equilibrium. Okay, so dynamic equilibrium. And what that means is that the forward and reverse reactions are happening at the same time. Okay, so dynamic equilibrium, that's where that's set up. So if we take something just as blatantly obvious as A plus B is in a reversible reaction, a dynamic equilibrium with C and D. Now, of course, when you start the reaction, these, okay, they're your reactants. So when you put those in, all of your material, if you like, is composed within those reactants. Once you start the reaction, of course, this forward reaction starts and we start producing C and D. Now, as that's happening, C and D are able to actually react together and go backwards to form A and B. So the equilibrium, that dynamic equilibrium, starts to be set up almost immediately. Now, maybe to start with, this forward reaction here has a faster rate than the reverse reaction, but it gets to a point where both of those reaction rates end up being exactly the same, okay? So a dynamic equilibrium is set up. It is at equilibrium when forward and reverse reactions are at the same rate. Okay, so the rate of the forward reaction equals the rate of the back reaction, whichever way you want to put it, okay? So that's when an equilibrium's set up. Now, really importantly, it doesn't always end up in the middle. It's not a 50-50 split between reactants and products. It's actually, it can lie anywhere. You know, 90% of your stuff can lie on the reactant side, 10% on the product side, or vice versa, and anything in between. So that's really, really important. You understand that it's not always perfectly balanced. It can lie to the left with our reactants, or it can lie to the right with our products. Okay, but what we can do, I mean, every equilibrium is different. Okay, let's say a carboxylic acid, so something like ethanoic acid, that lies really, really far to the left-hand side. So we get very few products over here. Most of it is over here. So only a few molecules. So this lies really far to the left-hand side. But then you get other reactions like, you know what, I actually think this one. So the Haber process, this one lies quite far to the right-hand side. Okay, so just naturally, each reaction is very, very different. Now, I forget who it was that asked the question. Let me just scroll up to the top again because you were straight in there. Uzwa. Uzwa was saying, well, how does temperature affect it? That's really, really important because essentially we can manipulate this equilibrium. We don't need to just accept that it lies to the left or lies to the right. We can actually change it by changing the conditions. We can shift it to the right-hand side, making loads and loads of products if we want. So if we wanted loads of C, that was our product that we want, we can actually manipulate it and shift it to the right-hand side. Now, there are a few things we can use to do that. Number one, we can change the concentrations, okay? So if we change the concentrations, we can affect which way the equilibrium shifts. So essentially what it boils down to, concentration shown by square brackets there. If we increase the concentration of A and B, or A or B, then it's going to shift to the right. Because what does Le Chatelier's state? Well, Le Chatelier's is all about these changes that we can make to manipulate this equilibrium. Le Chatelier states that if the conditions, you know what, I'm not going to write it down because you know what, it's going to take ages. If the conditions of an equilibrium in a closed system are changed, the equilibrium will shift to oppose that change. Now, to oppose that change, that is the most important part of that statement in Le Chatelier's, because whatever change you kind of force upon that equilibrium, it's going to do the opposite. It's going to try and bring it back down. So if we've increased the concentrations of A and B, then the equilibrium is going to shift to try and bring those back down to oppose that change that we've just done. Laura, yes, I can mention esters and carboxylic acids after equilibrium because that is linked to equilibrium. We'll put that all together. So if we increase A and B, it's going to shift to the right. How does it do that? Well, it actually reacts more of these together to produce more of C and D. So their concentrations will go up, and that lowers this back down again. So if you increase it, it will shift to the right and actually bring those concentrations back down again. It doesn't want loads of A and B in there. We've done that artificially. So it'll bring it back down by shifting it to the right-hand side. The opposite is true if you lower the concentration of something. So let's say I lowered the concentration of A and B, that will shift it to the left to try and bring those back up again. Once again, opposing the change. Second up, we have got concentration. We got, you know what, let's do temperature now, because that was a specific thing that Uzma was asking about. Now, for temperature, you need to know one piece of information. And without that one piece of information, you can't actually predict the change in the equilibrium when it comes to changing the temperature. So if I do another reaction down here, so I'm just going to use A plus B. No, you know what? I'm not going to use that. I'm going to use this one over here. So nitrogen, Haber process, because I actually know the value for this, 3NH2 in equilibrium with 2NH3. The one piece of information you guys need to know in order to predict what's going to happen with temperature is the enthalpy change for the reaction, which is delta H. That's the enthalpy change for the reaction. That is actually 92 minus 92 kilojoules per mole. That is the delta H reaction for the Haber process. Now this here, this is actually for the forward reaction. All right, so they'll just give you one number, and that's the enthalpy change for the forward reaction. So this is a negative number. What does that tell us about the forward reaction? You know what? The number doesn't actually matter. It's the sign that's really, really important. So what I can say here, because this is a negative number here, this forward reaction is exothermic. It's releasing heat energy. Now that is key. It's releasing heat energy moving forward. Now, what does that mean for the reverse reaction? Well, that's equal and opposite. If you know a bit of Hess's law, okay, and you know you can swap these symbols around on these delta H's, then you know that the reverse reaction is going to be endothermic. And endothermic absorbs heat energy. Okay.
Rich, I don't know whether this is useful or not here, and I hope it agrees with what you're saying. If in an exothermic reaction, is it useful in any way to think as heat as one of the products, and sort of in an endothermic reaction to think as heat as one of the reactants, and sort of in terms of which side of the reaction it sits on, or is that not useful at all?
I've never thought about it like that. It makes absolute sense, but I've never thought about it like that. Is that the way you learned it?
Well, no, the way that I have remembered it, whether I was taught it that way or not, I don't know. But yeah, I always think so. Exothermic reaction, one of the products is that it's producing heat, and then it helped me position or move the equilibrium. Well, if I add E, I'm adding more products, and therefore the equilibrium shifts in that direction. That's how I remember it. But
yeah, I mean, yeah, it would work. I think to a certain extent, what happens if they're flipped over? So what if it's an endo going forward and an exo going backwards?
Oh, I would leave that one to you to explain, because I don't know. Like, really, that was just the thing that was in the back of my mind. I thought I'd chip in. Like, that's how I remembered it. But there's no, I definitely wanted to run it past you, because I don't know whether that is like, whether it's.
I don't think that can be hard to pass. For this example, absolutely bang on. But I think if it was the opposite, if that forward delta H was positive, then it kind of falls down, doesn't it? You need to remember the opposite then, don't you? So
yeah, okay. Good point. So, I'll keep my mouth shut while I'm
actually. No, you're all right, dude. You're all right. I'm loving new ideas all the time. That's good. So our forward reaction is exo, and don't forget this releases heat. Now, if it releases heat, what's going to happen to the temperature? Well, the temperature is going to go up. So as that reaction happens, that forward reaction happens, temperature is going to go up because it's an exothermic reaction. Of course, the opposite way, endo, that's going to absorb heat energy. And if heat energy is absorbed, then the temperature is going to go down. So that's our link between That's our link between delta H and temperature change, okay? Now remember Le Chatelier's. If you increase the temperature, okay, Le Chatelier states the equilibrium will shift to oppose the change. So if you increase the temperature, the equilibrium is going to shift to try and lower it back down. Now, how can the equilibrium lower the temperature? How can it possibly do that? Well, it can do that by favoring the reaction that absorbs heat energy and bring the temperature down. So in this case, we go back to black here, back in black. If you increase the temperature, okay, let's say we've done that, that's going to cause the equilibrium to shift to the left, okay? So that's going to cause a left-hand side shift. Why? Because it favors the endothermic reaction, because Le Chatelier states it's going to shift to try and reduce the temperature back down, bring the temperature back down again, okay? So think of it like that. I mean, it's a bit complex, but at the end of the day, if you just remember, increase in temperature favors the endothermic reaction, okay? Increase favors endo, and obviously the opposite is true. A decrease in temperature favors the exo, because of course, if you bring the temperature down, the equilibrium wants to bring it back up again, opposing the change. So the only way it can do that is by favoring the exothermic reaction, releasing more heat energy and bringing that temperature back up again, okay? So Uzma, if you're still there, if I haven't put you to sleep, just put a couple of words in there just to say that hopefully that's helped. And like I said, these two statements down here, okay, if you remember nothing else, that one's specific to that one, but increase in temperature favors the endo, decrease favors the exo, and we need to know what they are. And somewhere in the question, if they're going to ask you about temperature, they have to give you that delta H, okay? They've got to give you that delta H. The last thing, just while we're on equilibrium, that can change it, ladies and gentlemen, is pressure. Okay, so pressure can actually affect the position of equilibrium as well, but
gases.
Yes, absolutely.
I remember.
So marks only if there's gases. So only if gas is present in the equilibrium. Okay, so if there's no gases in the equilibrium at all, then you can change the pressure all you want. Nothing changes at all. It will not affect the position of equilibrium.
Do they ever ask that, Rich? Do they ever sort of chuck in a pressure constant if there's no gas in the equation, or is that just like distraction tactic?
Absolutely, they've done it before. So if you've got, I've seen a question whereby everything's in aqueous solution. So essentially they'll ask you, okay, what happens if you change the concentration of this or change the concentration of this? What happens when you change the pressure? And of course the answer is nothing. And the reason is that there's no gases present. So pressure can't affect the equilibrium. So they can be sneaky like that. It's a good shout, mate. Equally, they can do it with part gases as well. So even if one of those products or reactants is a gas, then, pressure will affect it in some way, okay? So only if there's zero gases, no gases, there's no effect. But even if there's just one, then it will affect it. Somebody's ahead of me on here. Ali, it favors a side with the fewest miles of gas. I'm pretty sure you mean moles of gas. But yeah, absolutely, okay? So at the end of the day, bottom line is high pressure favors the side with fewest moles of gas, and low pressure favors the side, blah, 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 with the greatest moles of gas. Because if you increase the pressure, it wants to try and bring that pressure back down again. So essentially, it's going to favor the side with the fewest moles of gas, because if you've got less moles of gas or fewer moles of gas, they're causing less pressure. They're not banging on the sides of the walls of your closed system at all. So that's why it favors that side, to reduce the pressure back down and again, oppose the change. And of course, the opposite is true. Low pressure, it brings the pressure back up by favoring the side with the greatest moles of gas. And then, of course, that's going to increase the pressure. Taking our example here of the Haber process, okay, what this favors, on this left-hand side, all of these are gases, I should say, okay, and on this left-hand side, we've got a big fat 4 moles of gas. Over here, we've got 2 moles of gas. So what they're going to do is going to increase the pressure. And if they increase the pressure, it's going to favor that right-hand side, and you're going to get more ammonia out as a consequence. Okay, so increasing pressure, decreasing pressure, only where gases are concerned.
That was that classic
question now.
A GCSE question from what I remember. Maybe it was A-level, in like, because they do it at quite a high temperature, even though temperature favors the reactants. Yeah, you get a lower yield with high temperature in Haber-Bosch process, from what I remember. But they need to do it, and they use an iron. Is it an iron catalyst anyway? But they do it at whatever, how 200 atmospheres, 400 degrees C, or is it inverse of that?
It is. I think it's 350 atmospheres, 250 degrees, if you remember off the top of my head. But yeah, you're right. I mean, I think, you know, they would like to use a very, very low temperature because that would shift the equilibrium to the right-hand side and make you loads and loads of ammonia, increase the yield. Because so that because that exothermic reaction is the forward reaction, low temperature, happy days, loads of yield. But you'll have to wait like 6 months for it. And that's no good, because if you lower the temperature, the rate of reaction decreases, and it goes like about as quick as my nan does on a mobility scooter. All right. So they need to find a compromise. Okay. So they need to find a temperature where they get a decent yield. Okay. So it's not too high that you don't get a good yield, but it's high enough that you actually get a decent rate. But they can get over that. And Rich, you mentioned it with your iron catalyst. So your Fe solid catalyst, that doesn't shift the equilibrium at all. No catalyst does, but it makes things reach equilibrium a lot more quickly. So you get to the equilibrium stage a lot more quickly. So any changes you make, they affect the equilibrium more quickly as well. So catalysts really important, but they don't affect the position of equilibrium. Okay. So that's my kind of, rant on equilibrium and Le Chatelier's, folks. Hopefully, Uzma, I don't know whether you got back to me here. I'm just
there were lots of comments recently saying that they found it really useful, good explanation, yada yada yada. Ali said thanks very much. Can we recap the factors that affect KC and KP? Was a question from Sarah. I'll just run through a few questions, and you can maybe like pick the ones that are most relevant. Ali replied to that, favors the side with the fewest. Oh no, you read that one out already, my bad. Rich, what is absorbed when temperature increases so that the equilibrium shifts to the left? I don't know if that was talking about a specific example as you were doing it. What's absorbed when the temperature increases so the equilibrium shifts to the left?
If you increase the temperature, the equilibrium shifts to try and bring that temperature back down. So it does that by favoring the endothermic reaction, and that absorbs heat energy from the surroundings, and that brings the temperature back down. So it absorbs heat. So an increase in temperature favors the endo because that absorbs heat and brings that temperature back down. And again, Le Chatelier's to oppose the change. So that's it.
Rebecca asked us, maybe slightly different topic, or maybe you can put this on the back burner for later on. Please, can you explain how water can be different pHs? I assume have different pHs. My answer to that was, I'm assuming pure water, only H2O molecules will always have the same pH. I think that's pH 7. I don't know if it's bang on pH 7 or approximately pH 7. But if you can dissolve proton acceptors or proton donors into that aqueous solution, then the pH would obviously change. Was my answer accurate?
In a word, mate?
No.
Unfortunately not, no. Pure water can have different pHs. It depends on the temperature, and it is linked directly to equilibrium. So we stumbled upon on something really important here. I'll answer that KC, KP question in a word. The only thing that can change the value of KC or KP, the equilibrium constants for concentration and pressure, is temperature. That's it. Okay, so you can change the pressure, you can change the concentration, you can add a catalyst, you can do what you want. KC and KP for that equilibrium will stay the same. The only thing that will change the KC or KP value is a change in temperature. I'm not going to go into the details of why, that's for tutorials, okay? But temperature is the only thing that can affect it. But actually, two things then, just last things relating to equilibrium. Somebody mentions esterification. So we've got an acid, carboxylic acid, ethanoic acid, and let's do, I don't know, methanol just for giggles. This is in equilibrium. This is a really important one, okay? And we actually make an ester. In this case, it's going to be something like this. This will be methyl ethanoate, okay? Our sweet-smelling ester, and H2O is eliminated. Ester bonds found in what biological molecule, Rich?
I just muted myself just before that. That's fats.
Sorry, mate,
Yeah, so you have glycerol and fatty acid chains. You form an ester bond between them, and yeah, so lipids and fats is where you're going to come across ester bonds in biology.
Absolutely. Okay, so just testing you, buddy.
Yeah, I'm there. When I'm not muted, I've usually got something to say.
All right, so we've got our esterification process here, okay, in equilibrium. So that means, you know, all those same rules apply in terms of Le Chatelier's, all right? So forward reaction, that's what we want. We want to produce our methylophanoate. Now, what we do here is we shift the equilibrium. Quite sneaky, actually. There's a catalyst involved here, and that is conc H2SO4, okay, concentrated sulfuric acid. That does two things. Number one, it does catalyze the reaction. So the H pluses help that reaction happen and form the ester. So work in the same way as you'd expect any catalyst to do. But the second bonus thing here is that it's a dehydrating agent. Now, if it's a dehydrating agent, it removes water. Okay, when you're dehydrated, there's not much water in the body. Okay, so dehydrating agent, it lowers the concentration of water. It takes water out, and if you lower this concentration, how's it going to affect the equilibrium? It's going to shift it to the right hand side, and we're going to get more ester as a consequence. The other thing we can do is use distillation. Now, distillation actually removes the ester as it's produced. Okay, now as we do that, as we decrease the concentration of ester, if we're distilling it and evaporating off that ester as it's made, the concentration stays really low. And again, that shifts the equilibrium to the right-hand side, making more and more ester. So there's things we can do in organic chemistry in this particular reaction that link, again, directly back to Le Chatelier's. Now I'm going to rip on with that water comment, okay, just a quick one here. I'm going to change the color of my pen so you know it's something different. There is an equilibrium known as, that's not called that. It is basically H2O naturally exists in equilibrium with H pluses and OH minuses. Okay, so water naturally dissociates. If you take water at, say, room temperature, it's obviously pH 7. Now, I'm not going to go into it here, but actually the concentration of hydrogen ions is 1 × 10 to the -7 moles per decimeter cubed. So naturally, water does have a whole bunch of hydrogen ions in it. Okay, if you use that pH calculation to find the hydrogen ion concentration at pH 7, it's actually quite a high concentration of hydrogen ions. You don't think of water as being acidic. I mean, technically it's not, it's neutral, but there are lots of hydrogen ions and hydroxide ions in there. Now, I believe, and if I remember rightly, this forward reaction, because we need to break the bonds in the water, is actually, no, that's a big fat lie, endothermic. All right, so you need to put energy in order for that H2O to break up to H pluses and OH minuses. Of course, when they join back together, this is an exothermic reaction. So what's going to happen to pH? What's going to happen to the hydrogen ion concentration? Red vanquished, that is the equation in question. Brilliant. If you increase the temperature of water, if you heat water up, what's it going to do to this equilibrium? Well, if you increase the temperature, it's going to favor the endothermic reaction. Okay, so it's going to favor this reaction here. And what's going to happen to the hydrogen ion concentration? Well, hydrogen ion concentration is going to decrease. We're going to have fewer hydrogen ions. So what happens to the pH of water when we heat it up? It actually, becomes more alkaline. I think I've got that right. Off the top of my head, I'm pretty sure it's this way around. Okay, so hang on. What's going to happen? No, I've got it wrong. Excuse me. There we go. It's going to favor the endothermic reaction, which is not the backward reaction. Excuse me. Rewind. Forget I said that. I thought I was wrong. So if you increase the temperature, it favors that endothermic reaction, which means we're going to get more of these. That increases hydrogen ion concentration and therefore increases pH. So, no, it decreases pH. Come on, Rich. It decreases pH, so therefore it's more acidic. Blech. Sorry, guys, I'm talking faster than my brain will work. So yes, changing the temperature of water will change the pH of it. based on Le Chatelier's and this equilibrium with H2O, okay? And this equilibrium, that links to the ionic product of water and Kw. And when you learn how to calculate the concentration of bases and the pH of bases and things like that, you'll come across this. But this is quite an important one. It doesn't appear in all specs, okay? But it's a good one to know, okay? And it's a good link to Le Chatelier's and stuff that we've got there. Rich, did you see any other questions on equilibrium before we shift on?
I did. I was actually just writing a little Ronnie a note there. Let me.
Sorry, buddy.
That's all right. No, I was actually trying to do 3 things at once. I'm trying to answer my comments on my biology course. I was trying to ping Ronnie a note and read some comments at the same time. Yeah, lots of good comments about pHs and logs and all that kind of stuff. Logs are super confusing often in biology. The new A level requires knowledge of logs and things like that. They're not too bad, and Ronnie can probably explain it better than either of us. But yeah, just getting to grips with them, not ignoring them and trying to leave them to the last minute is my advice with logs. Like once you've got your head around what they are and how they work, then really not too bad. They're just a different way of like transforming data.
Yeah, that's it. Just it's like the way I see it, it's like a simpler form of putting data. When you've got a huge range, it brings that range right back down again to more manageable numbers. So that's where we do the that's where we get pH from, is like and pKa and stuff like that. Essentially in chemistry, you've got your log and your anti-log button. As long as you know how to use them, you're laughing.
Yeah, precisely. So Kane was just asking about, he's saying these sessions have been super useful. Thanks for that, Kane. And there's a bit of confusion there. Like from October onwards, all our like proper lessons so like we're going to have handouts, and then it's going to be like you're going to seek the schedule in advance. You can do all the questions in advance, and then we can tackle the questions. But from October, these sessions the full lessons are only going to be for our subscribers, our Ultimate Guide subscribers. So yeah, that's, if you want them to continue, then that's obviously where you're going to go find them. Sean asked us the question, Sean Casey, can you do a bit upon the rate of reaction equation and using the rate constant from a table of concentrations and rate of reaction? Does that make any sense to you? Shall I repeat the question?
Yeah, it does. So that's looking at orders of reaction and using the orders of reaction to find the rate equation. If I can find a decent question on that, I'll add it to the list to see if we get there. Yeah. So rate equation, no problem. So I reckon you got to do first come, first serve, don't we, mate? So
yeah, I'd say so, yeah.
Le Chatelier's check, benzene and isomerism, stereoisomers. Benzene's a whole thing on its own. Let's have a look at some stereoisomerism, folks. Okay.
And just before you jump into that, you can maybe have a quick think. I'm just going to do a bit more housekeeping. So Darshan asked us, do you guys do AS level AQA biology and chemistry videos? You betcha we do. All the courses we make are exam board specific, so you're going to be getting exactly what you need. And we do biology, chemistry, maths, that's year 12 AS and year 13 A2s, so all of those subjects are covered. There's a little bit of physics in there. There was a little YouTube live on that off on Monday. So you want to see what we can do in terms of physics, check out the YouTube live. Basically, all the courses are going to be fully complete and up to date by the end of the month. Ronnie's going to be doing some homework help in her web classes on Thursday. So if you want to join Ronnie in her YouTube lives and get some homework help, then Thursdays at 8 p.m. YouTube until the end of the month. I think that was more or less it. The free science lessons. Okay, we can deal with that in the chat actually. So Rich, I think we can go back over to you to handle that question.
Okay, Bonza. Right, so stereoisomerism. I mean, it's a little trickier than the other types of isomerism you're going to get in organic chemistry. But you know what? There's just 2 flavors, I think, just 2 flavors. And the first one is EZ. You would have come across this one, or you will come across this one, depending on where you are, in the first year. And it concerns alkenes. Okay, so alkenes, we've got a double bond there. The main thing here is that the double bond is non-rotational. Normally bonds can spin, but in a double bond, they actually can't, okay? Rich, for some reason, I think you're pinned on the camera there, mate. I keep looking at the camera.
Okay.
I'm not. Don't know why.
Did that work? I'll mute myself so there's no sound coming out of it. If not, I'll have a little play with Zoom. Sweet,
cheers, mate. So yeah, alkenes, double bond, non-rotational. So that's what creates this molecule whereby you don't get the flexibility of the groups on the 2 carbons spinning around. Okay. So what have we got here? Well, we've got 4 different groups attached to our carbons, 120-degree bond angle. Now, for EZ isomerism, you need 2 things. 1, C double bond C, check. 2, we need 2 different groups on each carbon in the C double bond C. So that's really, really important. So on the left-hand side here, let's go, I don't know, let's have a CH3.
Rich, I think maybe you've stopped your video, which is why it's not showing your video anymore. So maybe just check in Zoom that you haven't disabled your video, because I turned mine off and then we both disappeared.
Okay, so nope, it's not doing that. FaceTime HD camera built in. Maybe it's because I'm sharing my screen. Hopefully it's not because I'm sharing my screen.
No, it shouldn't be. I mean, it was working all the time. But yeah, when I disable my camera, we just disappear, both of us entirely. We can still see your screen actually.
Okay.
But
yeah.
I mean, it's fine. I'm sure they can handle not seeing you. You can just remember to stop screen sharing if you want people to see your face.
I think, yes, most people could handle not seeing me. That's
I wasn't going to say it, but yeah.
I'm just waving my hands at the camera and stuff as I'm explaining, but nobody can see. So there we go. So we got 2 different groups attached to each carbon. On the left-hand side over here, we've got a CH3 and a H. On the right-hand side, just for giggles, I'm going to put a chlorine and, I don't know, another H, okay? So importantly, as long as these 2 groups, okay, are different from each other, they can be the same on both sides. It can be completely symmetrical, this molecule, okay? But as long as this one is different to this one, and this one here is different to this one, then you've got the makings of an EZ isomer. Now, very quickly, there's rules, all right? Now, I'm just going to draw this molecule out as a displayed formula just so I can see the naming of it a little bit better. So I've got C double bond C, we've got a chlorine, we've got a hydrogen, we've got we got that. So we have got 1 chloro propanone. Okay, that's the name of this molecule. Now, the EZ isomers have the same name, okay? It's just the prefix is different. Now, what we need to look at are for priority groups. Now, you probably need to learn, I think 2 out of the 3 examples need to learn the Kahn-Ingold prelog system, which is a huge kind of kerfuffle about deciding which one is the priority group, looking at the atomic numbers of each of the elements as you go down the chain away from the carbon and the C double bond C. But the way I see it, long story short, unless you're answering a question on Kahn-Ingold, the basic thing is this, okay? Heaviest group equals priority. Okay, so you compare the 2 groups as a whole, whichever one's got the greatest MR as a whole is going to be the priority group. So the CH3 is the winner here because that's 15 and H is only 1. Chlorine is 35.5, H is only 1. So those 2 are our priority groups. Now it's where those are relative to each other that decides the prefix. And of course, you've probably all heard this, but the Z isomer is where your priority groups, like this one, are on the same side, okay? So this is your Z1-chloropropanone. If I was to draw the E version, all we need to do is swap out one side in terms of where the priority groups are. So that side's the same. All I need to do is swap the H and the Cl, and now we've got our priority groups on opposite sides, and that is the E version. No alliteration there or anything like that, okay? So Zs are on the same side, and the E are on opposite sides, okay? So like I said, Kahn-Ingold prelog, it's where you look at the atomic numbers, and whichever one's got the greatest atomic number, then that takes priority. But like I said, a shortcut when you're looking at these molecules, and you know what, there's no exceptions, the heaviest group takes priority. So the heaviest group out of the 2. So unless, like I said, you're having to explain how you did it, if you are having to explain how you did it, you talk about the Kahn-Ingold prelog. If you don't, and you're just deciding what the name of this molecule is, just use the heaviest group. It saves you a lot of time looking up atomic numbers and stuff like that. You probably just by looking at it, you'll be able to tell what the priority group is. So in terms of this, okay, somebody mentioned the pi bond before, okay? The second bond here is the pi bond. That's what stops it from rotating, okay? Organic chemistry is a no for me. I prefer physical chemistry. Well, you know what? You can't love it all. And if you do, then good luck to you. So next up, the other stereoisomer that we have is optical. Okay, now optical isomerism, really straightforward. What we need here is a carbon that is bonded to 4 different groups. Okay, 4 different groups. So you've got to have 4 single bonds around a carbon for a kickoff. So if I just drew a molecule like this, the simplest example of this is butan-2-ol. Okay, butan-2-ol will show optical isomerism. And if you look, and you're probably going to get quite complex ones in the exam, all you need to do is look for that one carbon, or maybe there's more than one, that has 4 different groups attached to it. Rich?
Is this to do with chirality?
Absolutely. That's one of my favorite words, that geek. Chirality.
Guys, A-level chemistry flooding back to me. I did my A-level chemistry in 2003 is when I did my A-level chemistry, and I haven't done any active study in that since then. So that's why there's a few holes in my knowledge.
Yeah, I was still in the 90s, just 99. I actually found my, where I worked in college, they kept all the old papers, and I've actually found the one I sat in 99.
No way. Do you know which exam board you did then, Rich?
WJEC.
Oh, you did? Okay, yeah. I have a feeling that I think I did EdXL biology. I get asked all the time, and to be honest, I really don't remember. My mum taught me A-level biology, and my mother taught A-level biology at the school that I went to. And yeah, I learned the subject I now teach from my mother. Rich, do you want to just try stopping your video and starting it again? I don't know why. It's just not showing that. I'm just looking at myself on YouTube right now, which is, yeah, not the worst thing in the world, but try stopping and starting and see if you can like boot me off. Because
yeah. So I don't know whether that's changed anything. It doesn't look like it has.
I'll mute myself and disappear.
Share screen just for a second. See if we can...
Yeah, try maybe popping out of that and just going, I'll mute myself so I go away.
Yeah, just bear with me a second. No, no, you're on full on and it's not coming to me at all now, is it? That's very weird. Spotlight video. Here we go. We're back on. This is me now. Brilliant. So I will share the screen back again and hopefully it doesn't mess it up this time. Tick tock, tick tock. And are we back? Yeah, we're back. You got me in the top right hand corner again. There you go. Have you got an iPad? Yes, you've got an iPad as well. Fantastic. Right, so optical isomerism. Rich is absolutely 100% correct, because if we look at the 4 groups that we've got attached to that carbon, okay, they're all different from each other. Now, that carbon is known as a chiral center. Okay, so that one there, I'm going to put a star. This is known as the chiral center. It's a molecule that shows chirality, okay, or optical isomers, or is optically active. Okay, so all of these words are really, really important. There's a lot of new words when it comes to optical isomerism, folks. Okay. So that's our chiral center. Now, how do we show the isomers? Now, remember, stereoisomerism is where we get groups that are in different positions relative to each other in space. This is a little bit more difficult, and this is where you need to draw a 3-dimensional tetrahedral structure. So, like we focused on the double bond up here to show EZ isomerism, we focus on that carbon that's the chiral center in optical isomerism. So I'm going to draw my 3-dimensional tetrahedral structure, 109.5 degrees, just so you know. Okay, you need to remember those. And we've got our OH, we've got a CH3, we've got a hydrogen, and we've got a C2H5. Now I always just shorten the groups just because it makes it easy, okay? So Ali's just asking, explain what exactly chirality is. Chirality is the, how can I put it? If it's chiral, then the 4 different groups can be arranged in different ways around that central carbon atom, okay? So the chiral center is just, all you need to know is that that's the word we use to describe that carbon that has 4 different groups around it, okay? And Kane, yes, you're absolutely on the right track with this. So this is one isomer. It doesn't matter where you put the groups in this, doesn't matter what order you put them in. What is important is how you draw the optical isomer of this, which is literally just a mirror image. Now, you don't need to be a decent artist to be able to do this. I'm just mirroring what is on the other side. Now, it doesn't look any different, but guaranteed It is different. So these are our optical isomers, okay? The only way you can show this is by drawing the mirror image of one and compared to the other, okay? So it's like your hands. If you're looking at me in the top screen up here, okay, these are essentially optical isomers of each other, okay, because they're non-superimposable. You can't put them over each other, but they are the same, okay, apart from the old wedding ring there, okay, but they are exactly the same. They are mirror images of each other. Okay, so that is your classic example of optical isomerism. You know, students are doing questions on it when they're doing this, okay? So they are optical isomers, also known as enantiomers, okay? Enantiomers, that is the posh term, if you like, for optical isomers, of which there are only two. Like E and Z, there's E and Z. In optical isomerism, there's L and D. Now, there's no way, I've just made this up, there's no way you can tell just by looking at the molecules which is the L and which is the D version of this butan 2O, not butan 2 and butan 2-ol. What you need to do is put them through a polarimeter. The L version will rotate polarized light anti-clockwise, let's say by a particular set of degrees. So maybe, I don't know, I'm just making this up, but 14 degrees. The D version will rotate plane polarized light clockwise by 14 degrees. Okay, so one rotates it clockwise. The D version, dextro-rotatory. Dexter means right. That's what my dog's called. I don't know. He's never. Is he right? I don't know. I don't know whether he's right pawed or left pawed, but there we go. So dextro-rotatory, 14 degrees to the right, or whatever number it is. Levo-rotatory, 14 degrees, or whatever number it is, equal and opposite to the left. Now, last bit on this, we can have a racemic mixture, okay, or a race mate. Now, this is where you have a 50-50, and really important term here, I'm going to put it in, what color haven't I used? Purple. Equimolar solution. Okay, that word equimolar, so you've got exactly the same number of moles in that solution of the L and the D isomer. That gives you a racemic mixture and has no overall effect on plane polarized light, because as one is trying to turn it clockwise, the other turns it anti-clockwise, and they just cancel each other out. Okay, so that is our stereoisomerism, the two flavors of stereoisomerism that you guys are going to come across. Okay, so all those key terms when it comes to optical isomerism, loads of key terms there, folks. Okay, I'm not sure. I don't think I missed any questions on this. It depends on your exam board whether you need to know L and D, but don't worry about it. Okay, just just check on your specification. But equally, you know what? If you're already signed up to the course, if it's in there, you need to know it. If it's not, you don't need to know it. Okay.
I say that all the time. I get questions. Do I need to know this? Is like, I definitely would not have created a lesson if I've cut out everything that can be cut out has been cut out. And sometimes I get, I've studied this in school. Do I need to know it? It's a bit more of a common question to get asked as well. Generally speaking, the opposite holds true as well. If I've not made a video on it, then it's something you don't need to know. Sometimes it's nice to know extra details, and your teachers just teaching to the exam all the time, if you were doing that with your students in your classroom week in, week out, could get a little bit dry and boring. So sometimes it's nice to elaborate and go into detail and explain the background behind something. But what you need to know for the exam is what we've put in our courses, and that's sort of what we specialize in. We had a question from Sarah saying, is this A2 organic for OCR? I don't think we've done it yet. I assume that was the chirality and the stereoisomerism you were talking about.
Yeah, it will be. Yeah, optical isomerism is in the year 2 of all the exam boards. So if you haven't done it yet, don't worry. Okay, I'm sure you will. I mean, whether you've actually started doing your year 2 organic yet, I don't know. I mean, it tends to be one of the first things you learn, but if it's not, I'm sure they will get to it. Maybe they've gone straight in with benzene or something like that, but yes, you will get to it. So don't panic. And like I said, it's in this course, and it's definitely in your specification. It's in all of them. So if you haven't done it yet, don't worry. Your teacher's obviously got a master plan that they're working to. Right, if I remember rightly, okay, like I said, I think the Arrhenius was a bit heavy for this evening. You know what? I will do that next week. That is the first on the list for next week, Arrhenius. All right, but you know what? We're doing a lot of organic, so let's look at organic analysis. So mass spec and fragmentation. I love this. This is, it's a sad thing to say, isn't it? But you know what? I think it's really, really important. Diagnostic tool when it comes to finding out the structure of molecules. Okay, so you know what? Let's do this. So mass spec. And you know what? Let's compare, and this is the one I've actually used in the tutorial. So you're getting a freebie here. Let's have a look at propanal and propanone. Okay, so these two molecules both have exactly the same MR. You know what? I can't do that in my head. So what are they? They are propanal, 1, 2, 3. So that's a double bond O, H. So this is an aldehyde. Okay, now we've got that aldehyde group on the end there, propanone. We've got that carbonyl group. That's right in the middle of the carbon chain here, okay? Oops. So these are both C3H6O. So I'm just going to add that up really quickly. 3 times 12 plus 16 plus 6, 58. Okay, so the MR of both of these is 58. So if you put these through a mass spectrometer, and I'll just draw these out like so. Okay, propanal on the left, propanone on the right. And if you remember, mass charge ratio on the bottom, and this is, I don't know, abundance, usually percentage abundance. We're going to get 2 peaks. We're going to get a peak on the end here and here. Now, both of those are going to be 58. Okay, why? Because that is our molecular ion peak. That is the heaviest peak we've got, known as the M+ ion. Ignore how high they are, okay, but they're both on the end and they're both 58. So that wouldn't tell us the difference between these two molecules at all right, because they both have exactly the same MR. What does help us distinguish them is the fragmentation. Now, when you put an organic molecule into a mass spectrometer, I mean, anything really, it gets vaporized and it gets ionized. It gets bombarded with electrons or gets passed through an electrical current, depending on which one you're looking at. But essentially, that can wreak havoc with the molecule, all right? It doesn't just nick off an electron. If it nicks off an electron, it could physically break a bond. And that's what actually happens, is fragmentation. These molecules are split into fragments, loads and loads of different fragments. There's no way of controlling it. It's like if you smash a plate, you drop a plate on the floor and it smashes, you've got no control over how many bits that plate smashes into. You can drop exactly like the same type of plate on the floor again, and it will smash in a completely different way. So it's the same as this. We're making lots of different fragments all over the shop, okay? Now, how these molecules split up, well, let's take a look at the simplest way in which they can break. This propanal molecule, it can break that bond there. So it can literally split into 2. So we're going to get 2 smaller peaks, or lower MZ value peaks. We are going to get one at 15. Why are we going to get one at 15? Well, that's because this is the CH3 bit here that I've just circled in red. So that's CH3 plus. Okay, and I shouldn't have done that. Let me get rid of my circle first. This is the CH3 plus. Now, don't forget, everything that comes from a mass spectrometer is positively charged. So the other part of the molecule, the C2H3O, that is, let me do quick maths, 43. Okay, so 43, we're going to get another peak, which I will draw in here. And that's, say, about there. Okay, so that's at 43, and that will be C2H3O plus. So this part of the molecule is going to cause that. So if it breaks in that bond, then those 2 peaks we're going to get. However, it could also break. Let me get rid of that and put this back to black. It could also break on this bond here, like so. Okay, so what we're going to get are another 2 peaks. We're going to get the C2H5. So that's 12, 24 plus 5. So at 29, we're going to get another peak here. Okay, so maybe about there. Okay, so this is at 29, and this is our C2H5 plus. And you know what? This is adds up to 29 as well. So we're going to get the COH plus as well. Both of those things cause that peak at 29. Okay. So we get 3 fragments. admittedly, we are going to get lots more. Okay, we can get a single hydrogen that causes an MZ peak of 1 and then a peak at 57. It can break in so many different ways. And if you look at the real mass spec of propanol, you're going to get loads and loads of little peaks all over the place because there's lots of different permutations of how that plate smashes. Remember what I was saying with that analogy. But we're just focusing on the main chunks here. And it's the main chunks, if you like, that can actually tell us the difference between propanol and propanone, because they both have that same M plus peak, all right? But when the bonds break, they end up with different fragments. So let me show you with this one. So in propanone, okay, this bond here can break. We're going to end up with, let's do a peak at 15 for the CH3 plus, okay, and that's the same as this one on the left, so CH3 plus, but then we're going to get a peak at 43 again, which is the same as the one on the other side. That is our C2H3O plus. That's this part of the molecule here. But you know what? If we get rid of that, okay, and we put that bond back, and this time we break this one on the right-hand side, well, we end up with exactly the same things. So there's no way you can break this molecule up to give a peak at 29. You are no peak at 29 here. So that is how we tell the difference, okay? So really, really important here, okay? Fragmentation can help us deduce the structure of a molecule. If there's a 15 peak, then you know there's a CH3 somewhere that's been broken off, okay? So that really, really helps when it comes to that. So fragmentation, really, really important, okay? And it helps you, like I said, deduce the structure of a molecule along with infrared spectroscopy and along with NMR. So I wasn't watching the comments on here, folks. I mean, has anybody got any particular questions about mass spec?
In fact, to be honest, I've been mostly just explaining a few different things. So people asking about, can they get combination courses for the starter guides? There's no, we looked at doing this, but if you think you've got biology, chemistry, and maths, and you've got starter guide and ultimate guides, there's like all the different possible parameters. Ronnie can give you all the numbers, I'm sure, if you want to, but there were just way too many combinations. I like starter for this and ultimate for that and starter for, like, it was just a minefield. So the only way to get a discount by getting combinations, of course, is with the ultimate guide. So if you're getting like biology and chemistry together, instead of being 49 and 49, it's 79. In biology, chemistry, and maths, instead of being 147, it's 99. So those three subjects, Darshan, I know, was it Darshan? I think it was Darshan said, what a rip when he first realized saw the price. But basically, you'll get each of those, you're going to get 2 hours a week with me doing biology, 2 hours a week with Rich doing chemistry, and 2 hours a week with Ronnie doing math. So if you're paying those sessions, we asked our students last year, what do you value those live sessions at? And I think it was 1173 was the mean, but just over a tenner. So you're getting 20 quid's worth of biology lessons, 20 quid's of the chemistry lessons, and 20 quid's worth of math lessons per week. So there's like £60 a week's worth of live teaching, and that doesn't, then you're getting all the course, all the documents. Like, there's so much in that course. I like, once you've seen it, you definitely won't think that it's not good value for money. And don't take our word for it. Ask other students out there. Check out what the reviews are saying. People genuinely have been using this by the hundreds and by the thousands of people bought my course last year. And just ask the other students, I'd say, stuff to that. Okay, going back to actually really reminiscent. This, sadly, it's actually been taken out of the spec. It was one of the most complicated things, but once you got your head around it, it was really cool. It was called restriction mapping in biology, where you have like an entire, it's usually a plasmid, but an entire genome, and you sort of break it up into different size chunks. You don't know where the breaks are going to be, but you can look at the relative different sizes of those chunks and then sort of piece the whole genome back together again afterwards. So really similar to this, like, you don't know which bonds are going to break or what size the fragments are going to be, but by looking at the different sizes, you can get information about the two different things, even despite their MRs being identical.
Yeah, that's it. I mean, just huge sets of data dealing with that. I bet. I mean, these are just really simple molecules as well. When you get to the more complex ones, I mean, some of the mass specs you see on them are just like, they look like the Alps. You know what I mean? It's just like
spike. Yeah.
But no, this is a really useful tool. This, and like I said, they like asking questions, linking this to, say, chromatography. So gas chromatography, mass spectroscopy, GCMS. So in year 2, you link these two things together. But even in year 1, you link this with IR to help you deduce the structure of a molecule, maybe some reactions and stuff like that.
Yeah, another quick question was, I think it was Hassan, or was it Wada Hassan, who was asking about with the combination courses you want to buy biology and chemistry together or biology, chemistry, and maths together. It doesn't ask for your exam board before the checkout page. It asks for your exam board after the checkout page. I know with the single courses, we can just give you biology, AQA, or chemistry, OCR. But if you're buying a combination, you buy the course and you say, which board do you do? And then we give you the courses that, obviously, if you're doing biology, AQA, we give you that course instead. So we're actually going to just make a little change on the website. You might see that happening at some point today or tomorrow, just to make that a little bit more obvious. When you actually chemistry questions, I've been sort of answering questions.
No, don't you worry about it. It's fine. So I reckon we've got time to sneak one more thing in. I mean, since we're talking about analytical techniques, I know somebody was really keen to talk about, say, NMR, nuclear magnetic resonance spectroscopy. That's really, really important diagnostic tool, again, in year 2. I think it's WJEC. In Wales, they make them learn this in the first year, but the low resolution version, and then you learn the high resolution in the second year. But you know what? Everyone who's doing AQA, OCR, and Excel needs to know this for the second year. And you know what? It can be a little tricky, and it does confuse a lot of students. And for that reason, they put it in one of the end questions in the exam a lot of the time, okay? But long story short here, okay? NMR, what we've got along the bottom, okay, this is our chemical shift, usually signified by a sigma, okay? So it's a little delta, I do apologize. So this is our chemical shift. Now,
is that nuclear magnetic resonance? What does MNR stand for?
Yeah, nuclear magnetic resonance. So essentially with hydrogen, because it's got an odd number of protons, so it's obviously H1, what we've got is that proton can spin one way or it can spin another. So what they do is they put it in a magnet, and these proton spins line up with the magnet. So essentially what we're looking at here are hydrogen environments, hydrogen groups. We can tell whether there's a CH3 or a CH2 or an NH2 and stuff like that. So yeah, none of the specs actually require you to know how NMR works. But you know what, when I do the tutorial on this, because this is the one that's coming up Friday, I'll be writing this one. I will do a little bit of a background on it, because I think it's important just to know where this information comes from. So at least when you start looking at the data, you're like, oh, right, that makes sense. So yeah, nuclear magnetic resonance spectroscopy. Also comes in carbon-13 flavor. All right, because there's an odd number of not of protons, but an odd number of nuclei components, so protons and neutrons.
And who was it? It was AJ who said, can you explain the carbon-13 and proton NMR if there is an exam question on it? I guess, is that what you're doing right now? Is that?
Yeah, that's it. Absolutely. Yeah, because I think he asked me, yeah, I got that right from the start. So yeah. So where do we start? Chemical shifts. Number one, let's say we get some peaks here, okay? So I'm going to draw just a random peak here. I'm not using an example of a molecule. In fact, will I use an example of a molecule? No. So let's say you get something like this. I'll tell you what, let's do a quartet. Let's undo that. Let's do a quartet here, like so. I'll tell you what, let's draw the molecule, because it does make life easier. Okay, so like this. Okay, so you're going to get a high resolution. Okay, now of this is ethanol, of course, nice and straightforward. We're going to get these peaks, so just bear with me a second. You're going to get this one here, and you're going to get a triplet, which is kind of like this. Okay, now I don't know the chemical shifts off the top of my head, okay, but like infrared spectroscopy with HNMR, we won't have time. Carbon-13 is very, very similar, but with HNMR there is a lookup table. Okay, so the first thing you should look for, okay, is the chemical shifts in the table. That will tell you what type of hydrogen you've got, whether it's a hydrogen that's in an alcohol group, whether it's a hydrogen that's in a carboxylic acid group, or indeed, you know, an amine group or something like that. Where it lies on here, that's a really good indicator. So you can look that up in your data table, no problem, and that gives you an indication. The second thing, let me just undo that. The second thing that this can tell you are the peak heights, the relative peak heights, okay? So relative peak heights, now it's not about the number on the value, okay? It's about the relative peak heights. I'm going to say this is, and I've drawn it in a 3:2:1 ratio. If you imagine these as not being split and they look like this, okay, you can see the relative peak heights going on here. What does that show us? That equals the relative number of hydrogens in that environment. Now, when I speak about environments, it's where on the molecule do those hydrogens live relative to everything else, okay? So that's what I'm talking about in terms of environments. Let me get rid of my scroll here. So we've got relative peak heights 3:2:1. Now, in this case, that is the actual number of hydrogens that exists in those different environments. It could be, just could be, that there's 2, 4, and 6 hydrogens in those environments. In this case, there's not. Don't forget, it's a relative peak height, but they can show you the exact number as well. It really depends on the molecule. So this peak over here on the right-hand side, okay, this one over here, that, I'm going to call this peak C. B, and A, just for reference purposes. Peak C is caused by this part of the molecule here. Because there's 3 hydrogens in there, that's why it's got a relative peak height of 3. This one here, B, okay, so that is C there. B is caused by this part of the molecule here, the CH2, which is why it's got a relative peak height of 2, so that's the B. And this single, poor lonely hydrogen over here, that's represented by this peak over here, the A peak. Okay, so 3:2:1 ratio. So last thing, it can show you the splitting, okay? Now the splitting of the peaks, that focuses on the hydrogens on the neighboring carbons, okay? So it can actually tell us not only how many hydrogens you've got in that environment, but how many hydrogens are in the environment next door, all right? So this is really like delving into the molecule and giving you lots of really good information. So the rule here, I'm going to put this in purple, is the N+1 rule, okay? So the N+1 rule, really, really important, really shocked face, got to remember that, because this is what's known as a triplet. Why is this? Okay, peak height 3, we've got 3 hydrogens in this environment, don't forget. It's a triplet because next to it, we've got a carbon with 2 hydrogens attached. Now, because there's 2 hydrogens attached to this carbon, this becomes a triplet. Remember, 2 hydrogens, the N+1, that's why this is a triplet, because the carbon next door has 2 hydrogens attached. Okay, so that's what the splitting is all about, its neighbor. This one here, this is a quartet. Okay, this is a quartet. Why? Because the hydrogen, the carbon next door, has got 3 hydrogens attached to it. So again, the N+1 rule, 3 + 1, it gives you a quartet. Now this one is a singlet. This one's a singlet because, well, it's not actually bonded to a carbon. It's bonded to an oxygen. There's no other hydrogens bonded to that oxygen. So 0 + 1 equals 1. And that is our singlet. So these 3 things here, okay, are the 3 things that your high resolution hydrogen NMR can tell you. Okay, so that's HNMR. Carbon-13 NMR is pretty much exactly the same, okay? But you're not going to have to deal with the splitting in carbon-13 NMR. It's more about the lookup table and the chemical shifts. So I'm not going to go into that now, maybe save that for another day, but essentially that's your HNMR. Not scary at all, I think, as long as you've done a few and you've seen a few questions and you can work your way through it and it'll help you decide on how that molecule looks. I've got loads of awesome questions I'm going to put in the course on using organic analysis to find the overall structure of a molecule, to test you in different ways, talking about, using chromatography, NMR, infrared spectroscopy, mass spectroscopy, wet tests. Brilliant. Loads of questions on that to get your teeth stuck into on the course.
Yeah, and I mean, we're all going to tell you the same. You're going to have lots of repeating advice from all the TT teachers this year, and like questions, there's no replacement for doing questions. You can learn all the material, but until you actually put it in the context of an exam question to sort of see how you're going to actually get tested on it at the end of year 13, that's the best. Just like the ultimate test is going to be, can you do the exams? And like, no matter how well you know it, sometimes you just got to do that past paper practice. There was a question back ages ago. In fact, someone was asking me, had you ever done any sort of industrial chemistry stuff, Rich, or have you always just been a teacher? I should know the answer to that, but I thought I'd put it to you.
No, I've never worked in industry. I went to uni and did pharmacology. So I worked in research, in pharmacological research for a year. But after that, I fell into teaching and I've never looked back. So no, I've never been in industry. There
was a question about, there was one about transition elements and colors. I'll maybe come back to at the end because that was slightly off topic.
That's a whole hour.
Yeah, that's maybe not maybe a next week kind of thing, or like come along next week. And obviously, if you want to join the web classes throughout the year, then they'll be there. Or check out the videos in the course and use the coupon try it free. Ali asked one quick thing about what you're talking about the splitting on NMR. How do you know which carbon the rule N+1 is talking about? So I didn't read that very well. When talking about the NMR, how do you know which carbon atom the N+1 rule is talking about?
Yeah, no problem. I mean, essentially what I think Ali's talking about here is, so if you've got, I'm just going to draw out ethanol again. So when we're looking at, say, let's say this carbon here in the splitting, do you look that way to see, how many hydrogens are attached there, or do you look that way? There's two schools of thought here, and unfortunately it does come down to your exam board. With some exam boards, what they say, I can't remember off the top of my head which ones, maybe I'll have to check, but the majority rules, okay? So first school of thought is majority rules. So if you've got, I don't know, a molecule like this, which is, I don't know, maybe you got two chlorines and a hydrogen there. Do you look left or do you look right when focusing on this central carbon? Because if you look right, it's going to be a doublet. If you look left, it's going to be a quartet. You will go with the quartet. However, some exam boards, they ask you to put them together. So you end up with a multiplet. So you'll have, 3 + 1, which is 4. So you'll have a 5-peak thing going on, which is a multiplet. So it really depends on your exam board. Some want you to use majority rules. So that will just be the 3, you'd look left. And some will want you to cumulatively put those hydrogens together and form a multiplet. So check your specification for that one. Sweet. Right. I'm sorry we didn't get through everything, folks. I know you had some other questions on here, like Richard's mentioned transition metals. That's a thing all on its own. I promised Arrhenius next week. It's nobody's favorite thing, but we will have a look at it. And rate equation. You know what? I think we pretty much got next week sorted already between the Arrhenius, between the rate expression. I'll look at an example question there. Okay, there's some brilliant example questions we can look at with the rate equation and colors of transition metals. That's a tough one because each of the exam boards are all different when it comes to which ones they want you to blooming learn. So I'll do my best. I think we'll focus on the ones that are current for all the exam boards rather than muddy the waters here, I think. So
yeah, and maybe when that situation does arise, then we can often look at like what are the underlying principles and we can pick.
Sure. Yeah. Oh, absolutely. Yeah. I mean, because we all need to know what ligands are and how complex ions are formed and substitution reactions, bidentate and multidentate ligands. We can certainly focus on that. But what I might do actually is just put up I'll make a spreadsheet and I'll just say, right, these are the ones you need to know for each of your exam boards so they can take a snapshot of it or something like that. But I won't spend any time talking about the colors. You just need to learn them, unfortunately. It's just one of those areas in chemistry, like your reagents to convert one organic molecule to another, like your shapes and bond angles in VSEPR. It's just one of those things where you just have to parrot fashion learn it. And yeah,
Do you
unfortunately,
want to pull your screen share so we can just see and say toodaloo, sign off?
yep. I will stop.
Lots of people saying yay because they don't understand the Arrhenius equation, so that will be helpful for them. Sarah's saying she can't wait. Maybe that's a little bit bold, a little bit strong, but yeah, we'll be here same time next week for chemistry, and obviously more. Yeah,
that was me. I'm trying to put you on spotlight video. There we go.
Yeah, so essentially all of those bits and pieces are going to be done as of in 2 weeks, not next week, but the week after. We're going to have loads of people in our YouTube live. So you regulars are going to be like blown away by what's that. We've got a little trick up our sleeve, but we'll keep that under our hats for the time being. So it'd be nice for you to all to come back next week. We'll help you out as much as we can and save up those questions. If you're getting stuck on something, we're here for this month to help you, to give you a little flavor of, you know, how we can help. And basically, yeah, save up those questions so you can put them to us, challenge us.
Absolutely, absolutely. Just to answer a couple of last questions on here, Rich, how closely alike are the 3 exam boards for chem? 90%. It's little details, little annoying details, actually, I found when I was writing the course, that are different between the exam boards, the way in which they want you to write the answers and stuff like that. But the content, largely exactly the same. Okay. Mick has asked me a couple of times, and I am coming around to answering you, mate. Is pharmacology more like organic chemistry? Loads of it, mate. Absolutely loads of it. Because I mean, at the end of the day, all these drugs, they need to interact with cells, they need to interact with tissues and bacteria and so on and so forth. They're all organic molecules. And talking about optical isomerism, if you're interested in that sort of thing, look up the thalidomide story. It's nasty, okay? So if you're squeamish, stay away from it. But optical isomerism in drugs and stuff like that, really, really interesting topic. So yeah, pharmacology, loads of organic chemistry. And I do regret, after doing all that, I preferred all the chemistry side of stuff when I went to uni. So that's hence why I've come back and started teaching chemistry. But yeah, it was really interesting, pharmacology, really, really interesting, but loads of chemistry.
Well, I think that's about it from me. At least I'll sign off to say, basically, cheerio. See you. Well, we'll probably be online, or I will be online with Ronnie. Ronnie's sessions tomorrow, 8 o'clock, doing some maths. She will help you out with your homework questions. Basically, any things you're stuck on, any sticking points, and she'll answer any of the questions that you've got about starting the new A level or starting year 13, any of that kind of stuff. So I'll sign off and leave you with Rich just to say cheerio, and then that's about us done.
Cheers, Rich. Okay, folks, thank you very, very much for coming along tonight. You've absolutely made this, because you know what? I had a couple of questions all planned out, but I thought, well, maybe I'll just need to go ahead and do those. But you have definitely kept me busy, more than busy. So I promise Arrhenius next week, rate equation next week, colors of transition metals we will touch on, but ligands and complex ions and stuff we definitely will do. So thank you very much for joining me tonight, folks, and spread the word. Okay, I don't want you to keep us to yourselves like your own little pet. All right, I want you to spread the word to all your friends. Get them involved over the next few weeks in September, so they can have the benefit of as well. They can ask us any questions they want. All right, thank you very much, everyone, to get involved, and I will see you on Monday with the rest of the guys. But enjoy maths tomorrow, and I'll see you soon. Bye.